Howdy everyone, my name is Atiana Bruce and I am an undergraduate researcher in the Chemical Engineering Department at Texas A&M University. My project this summer is entitled An Analysis of the Corrosion Preventative Capabilities of 2D Nanomaterials. Before I begin, I would like to thank my sponsors, the A&M O-REU program, as well as Los Alamos National Laboratories. I would also like to thank my mentors, Dr. Micah Green and Dr. Jody Lukenhaus from Texas A&M, as well as Dr. Hisato Yamaguchi from Los Alamos. I would also like to thank my graduate student mentors, Ian Eccles and Alexa Easley, and I would like to thank the entire Lukenhaus Lab group for helping me with this project throughout the summer. So to start off, I would like to go over my motivation and primary goal for this project. The remedy to corroded infrastructures in electronics is an extremely costly endeavor, scaling up to trillions worldwide, but in the USA, about 3% in gross domestic product is spent annually to remedy corroded infrastructures. So our goal is to make a nanocomposite coating that is scalable, non-hazardous, and acts as a good barrier for protecting metal against corrosion. So to do this, we have chosen an 80-20 ratio of montmorillonite clay, MMT, composited with polyvinyl alcohol, PVA, to make a nanocomposite that was airbrushed onto aluminum alloy coupons, which will be referred to throughout this video as AA. What is montmorillonite clay? Montmorillonite clay is a mineral in the phyllosilicate group, which is a smaller portion of the smectite group, which contains minerals such as talc and mica. So on the right-hand side, you can see MMT's chemical structure with the basal spacing equaling 1 nanometer, which is why MMT is referred to as a 2D nanomaterial. In between the layers of MMT are water molecules and interchangeable cations, which in this case were Na+. The benefits of using MMT include good dispersion capabilities, and it is consistently reported as being an effective gas barrier in literature. Furthermore, when you combine montmorillonite clay with a polymer, it creates a PCN brick and mortar structure in which the MMT physically protects the aluminum by providing alternative tortuous pathways for any permeating oxygen gas. In addition to this, polyvinyl alcohol will act as a physical barrier, decelerating the corrosion process through surface buffering. So it acts as a barrier for the aluminum from the NaCl electrolyte solution, which will induce corrosion. So in the upper image, you can see that the image has panels A, B, and C. In image A, the polymer is combined via mixing with MMT over a stir plate. This is solution processing. The reason why branched polyethylene, BPEI, is used in this image instead of polyvinyl alcohol is because this image was created by Pilar Suarez Martinez, who was the primary author in her paper, which is cited down below. This is the paper that we primarily based my summer research on. However, instead of branched polyethylene, we decided to use polyvinyl alcohol. And panel B is the airbrushing method, in which the PCN coating is formed over the aluminum alloy over a hot plate at around 70 degrees Celsius. Panel C is just an image of the brick and mortar structure. In the right-hand side is polyvinyl alcohol's chemical structure for reference. So our primary method throughout the summer has been airbrushing the coating onto the metal. The benefits of airbrushing include scalable production. It creates pinhole-free coatings. It has a low environmental impact and is safe for human use. In addition to this, it is rapid to produce. So it's about 40 times faster than any sort of spray-assisted layer-by-layer assembly. So on the right-hand side is an image of the bare aluminum alloy, AA, on the left, and on the right is the 80-20 ratio of MMT PVA coated AA. After we airbrushed our coatings onto the aluminum alloy coupons, we began electrochemical testing. So with this testing, we did 2 different tests per sample: open circuit potential, OCP, and electrochemical impedance spectroscopy, EIS. OCP basically checks the voltage status of the sample during its equilibrium stage to make sure nothing is wrong before we do EIS tests. EIS is used to determine the resistance of the film throughout the corrosion process. On the right-hand side is just an image of a Interface 1000 Gamry, just like the one we use to take our OCP and EIS measurements in the lab. So attached to this Gamry is a wire set containing different alligator clips. The red alligator clip is hooked onto our counter electrode. The green and blue alligator clips are connected together and are then attached to our working electrode, which would be the aluminum in the coating. And the white alligator clip we used for the reference electrode. All of our samples were exposed to 3.5 weight percent NaCl solution throughout our experiment. So I would just like to next go over the general paint cell assembly that we use for our experiments. So in image 1A, you can see a picture of the saturated column electrode that we used as our reference. Image 1B just explains further a little bit about what is inside each reference. So you have a platinum wire that goes through and is filled with saturated KCl solution. At the bottom of the reference is a porous salt bridge through which solutions can flow to and from the reference. In image 2 is the platinum counterelectrode, similar to the one that we used in our experiments. And on the right-hand side, you have a representative paint cell, whereas instead of the graphite black rod that you see in the image, we use the platinum counterelectrode that you see in image 2. So as I mentioned before, the electrolyte solution we use to induce corrosion is 3.5 weight percent NaCl. In addition to this, we covered our cells with Faraday cages and a foil-covered box to prevent excess electromagnetic interference or noise from different instruments in the lab from interfering with our data collection. These are the Nyquist plot results for a representative control cell which only used bare aluminum alloy versus a representative coated cell. In both of these graphs, there are a zoomed out version of the data and there is a zoomed in version of the same data but on a smaller scale. So if we look at the zoomed in versions, the two parts of each data plot can easily be seen. These two parts for each data plot are the semicircle and the Warburg tail. If we take a look at the left-hand graph in the zoomed-in version, the semicircle phenomenon can most easily be seen in days 3, 0, and 12. However, if you take a look at the right-hand graph, zoomed-in version, this semicircle is most prevalent in day 0. The Warburg tail is the part of the graph which extends out of the semicircle towards increasing Z double prime value. The takeaway from these graphs is that the Nyquist data for the representative 8020 MMT PVA coated alloy cell changes less dramatically over time. What is meant by this is that from day 0 to day 12, there is a steady increase in the diameter of the semicircle, giving way to a larger Warburg tail. However, if you take a look at the bare aluminum alloy control cell on the left-hand side, there is a dramatic jump in the amount of Z prime data points from day 1 to day 2. In addition to this, after day 2, there's a great decrease in the size of the Warburg tail, giving way to a smaller number of Z prime data points. In addition, one observation that can be made from the bare aluminum alloy graph is that initially in day 2, it can be seen that the diameter of the semicircle has increased. However, unlike the coated cell, by day 12, the diameter of the semicircle has decreased significantly. This communicates that the representative control cell has corroded significantly, whereas the representative coated cell has not. Here we have the Bode plots for the same representative control and coated cell. So we have 4 panels displaying 4 graphs. Panel 1A and 1B are for the representative control cell, and panel 2A and 2B are for the representative coated cell. Once again, this coating was the 80-20 ratio of MMT PVA. Next, we have an OCP versus day graph for the coated and non-coated cells. So the trend you can see with this graph where the OCP is versus SCE reference in volt is that as the aluminum corrodes, the OCP becomes increasingly negative. However, we can see that with the blue data points, the MMT PVA coating protected the aluminum alloy against corrosion. This is evidenced by the fact that the OCP values are in fact less negative than the bare aluminum alloy values. In addition to this, over the 12-day period, the change in the coated aluminum alloy OCP is more consistent than for the bare aluminum alloy samples. On this slide, we have displayed the visual images of the control samples versus the 8020 MMT PVA coated samples. On the top row, there are bare aluminum alloy control samples 1 through 3. On the bottom row are the coated samples using our MMT PVA nanocomposite. So all of the assembled coupon images are taken after 12 days of exposure to 3.5 weight % NaCl solution. However, the bare aluminum alloy image on the far left-hand side of the top row, as well as the 80-20 MMT PVA ratio coated aluminum alloy image on the far left-hand side of the bottom row, are taken on day 0, just before assembly. So as you can see in the top hand row, especially in control samples 1 and control samples 2, after 12 days of exposure to the electrolytes, significant amounts of white corrosion products have formed, as well as oxygen gas bubbles. However, as you can see in the bottom row, for samples 1 through 3, even though there are a little bit of white corrosion products, the coating has protected the aluminum alloy from forming significant amounts of corrosion products, and there are almost no oxygen gas bubbles. In conclusion, the bare aluminum alloy coupons corroded significantly after 12 days of exposure to 3.5 weight % NaCl solution. But our airbrushed 80-20 ratio of MMT PVA nanocomposite coating prevented the aluminum alloy from forming as many corrosion products or as many oxygen gas bubbles over a 12-day time period. Future electrochemical tests, including OCP and EIS tests, will be conducted using 4 mg per mil 80-20 ratio of MMT polydopamine nanocomposite coatings. Thank you.